syllabus for the syllabus for the next class test will be only the linear algebra portion, as you said. Is the first thing. And the second thing, since we have a limited class left, that's why I decided not to cover the uh, integration part. Also, some of you are, because the part we have, that is an analytical approach of the integration, and that also may not be very much useful for the people who will not take mathematics in future, because it's little different, the concept of why those integration uh, uh, give some value, or they converge to some values and so on. So this is the application of the analysis for construction of the integration formula. And the people who will take mathematics, this will be covered in detail. So that's why I thought that, okay, so that portion may not be important at this moment when we have limited class. So that's why I thought that I don't hurry up and take the same pace that for completing the linear algebra portion. Okay, let's. I wanted to give you two examples about these linear transformations. So that's why, but I could not do that because of the time. So let's just little bit recap that we discuss about the linear transformation for the general case. So here T is a linear transformation or linear map from V to W, where dimension of V is n and dimension of n is m. And VB is the basis, and V of V, and BW is the basis in W. So we want to then construct a transformation matrix of T with respect to this basis. Okay, that means, what does it mean? That means if somebody give you a vector in V, the coordinates will be given with respect to BV. Then if you multiply that vector with that matrix, it will give you the transformation with respect to the linear transformation T. That means it will give you another vector in W and with the coordinate system with respect to BW. Okay. So to do that, what we said that here the important part is that whatever the V1, V2, Vm, these are given the basis vectors. The coordinates of these vectors usually given for the standard coordinate system. And also same for the W1, W2, okay. Now we want to see that if we have a formula for the linear transformation T, that where do these V1, V2, Vm go out? That's why we get out T Vi, and where does it go? But whatever the after the transformation, whatever the vector will get, we have to express that vector in terms of the coordinate system with respect to BW. Fine. Whatever the vector we get, that should be expressed as linear combination of W1, W2, Wn, right? And from there, yeah, you can see that from there we get T V1 is this T V1 transformed, and this we express as a linear combination of W1, W2, Wn. These the coordinates of that vector after the transformation with the, and in this way we get all the coordinates after the transformation, and these coordinates will be written column wise. These coordinates will be written column wise, and then we'll get the matrix. Fine. So this was the main idea, and we had an example. There, a linear transformation was, the formula was given, and we had to figure it out that what will be the transformation matrix with respect to given basis for two different domains. Fine. In this case, the formula of the vector was given. Now I give you an example where the formula of this vector is not given. Instead of the formula, we have something else. And now from there, how to find out? Okay, so this is on oh, I have a time lag. Let's say we have a linear transformation T. This maps from R3 to R2. Okay, and the matrix of T relative to the ordered basis ordered basis. So one ordered basis should be given for R3. Let's say 0, 1, 1, 1, 0, 1, then 1, 1, 0. This is of R3, and let's say 1, 0, 1, 1 of R2. This is so with respect to this ordered basis, the transformation matrix is given like 1, 2, 2, 1, and 4, 0. So instead of giving the formula, transformation matrix is given. Okay. Now we have to find the ordered. What we have to find the ordered basis. Sorry, we have to find the matrix with respect to different ordered basis. Let's find the matrix of T relative to the ordered basis for the left side domain R3. Let's say the ordered bases are 1, 1, 0, 1, 0, 1, 0, 1, 1 of R3 and 1, 1, 0, 1 of R2. Okay, is it clear the problem? So we have a linear transformation, we don't know the formula. With respect to a set of ordered bases for both the domain, the transformation matrix is given. We have to find the matrix for a different set of ordered bases. So let me know if you have any doubt about this problem. I hope that you understand the problem clearly. Now we go for the solution. Okay. So first of all, what is our goal? Our goal is to figure it out where does this, okay, let's use different color. Where does these basis vectors go after the transformation? So that means we have to figure it out. That means we have to figure it out t of 1 comma 1 comma 0. But whatever the transformation we get, the coordinates we have to represent with respect to this ordered basis 1 comma 1 and 0 comma 1, right? And that coordinate will be the first column of that matrix, right? Now to get this one, we have to know the formula, but we don't know the formula. What we know the matrix, but this is not the matrix for this transformation with respect to the standard coordinate system. So that means we have to find the formula of this linear transformation with respect to the standard coordinate system or with respect to the standard basis. So how to do that? Okay. First of all, let's take, if you take any vector, let's say x, y, z. Let's say this belongs to, I mean, this is with this coordinate with respect to the standard coordinate system. Okay. Now we can express this with, let's say, some constant. Let's express this with respect to the given coordinates. Let's say with these coordinates. Okay, let's give some name of this one. Let's say I call this basis B3, this basis B2. Let's say this basis B3 prime and this basis B2 prime. Okay. Now what we have to do, that we have to figure it out. Okay, so first of all, we express this in terms of the coordinate system. Let's say C1, C2, C3. These are the coordinate system with respect to the basis B3. Okay. Why you want to do that? There is a reason, because if we know the coordinates with respect to B3, we know the transformation matrix, right? Then we can apply this transformation. There will be a chance to apply the transformation. So to do that, then we have to express this as a linear combinations of this basis vector B3. That means this 0, 1, 1 plus C2 into 1, 0, 1 plus C3 into 1, 1, 0. Right? And now, then we can apply this transformation. Let's say x, y, z. In that case, C1 will be 0 comma 1 comma 1, C2 into 1 comma 0 comma 1 plus C3 into, sorry, T of 1 comma 1 comma 0. Okay. Yeah, please just wait a minute. I take your question. I just complete this portion. Okay. Now, next problem is then how to figure out this one. Okay. But we have to figure it out the value of this one. That means if we apply the linear transformation on this vector, the coordinates of this vector is given with respect to standard basis. So whatever the vector we will get, we have to represent also with the standard basis, because we are going to find this formula, this the linear transformation formula for the with respect to the standard basis. Okay. So now, okay, at this moment we cannot do that. Let's give name like 1. So then how to figure it out? What will be the value of this with respect to the standard basis? First of all, uh, what will be its, which kind of vector will it give after applying this linear transformation? It does not matter in which coordinate system. Can we say that? Can we find what will be the value, or what will be the vector after the transformation is applied on this vector? That can be done. We know that this matrix is given, right, for the linear transformation. What is this matrix? If you remember, this matrix is that we are expressing the linear transformation from the left side that with respect to the coordinate system B3, on the right side with respect to the coordinate system B2, right? And how does, or how did we construct this matrix? What will be the every column of this matrix?
Transformation of the basis.
Right. So that means if we apply this linear transformation on this, what should we get? The first column of
First
that.
column.
Right, very good. The first column of that given matrix. First column of that given matrix. The first column of that given matrix is 1 and 2.
Yes, sir.
Right? It was given. Okay. But it was, okay, I write down 1 comma 2. So let's write in terms of the vector. But it was given with respect to which coordinate system? Standard coordinate system, or with respect to a different basis?
Different basis.
What was that basis?
That 1 comma 0 and 1 comma 1.
Right, B2. Right, right. Very good. So this was actually with respect to B2. But we want to figure it out. This is with respect to the standard basis.
Standard basis.
Right. So how, right. So how to figure it out? Okay. So this is with respect to B2 means this can be expressed the linear combination of 1 into the first basis vector in that set, that is 1 comma 0, plus 2 into the second vector.
Sir, it will be minus 1, I think.
Second vector is 1 comma 1, and this is equals to 3 comma 2. Sorry, which one is minus 1?
The first one. Minus 1 into 1 comma
I could
0.
not. No, it was given in the matrix. The first column is 1, 2,
Yes,
right?
sir.
So this is then 1
Yeah,
comma 2.
but we're getting 3 comma.
We are getting. I could not get your point. Can you please elaborate your point?
We're getting 3 comma 2 here, no, sir.
Right, we are getting 3 comma 2.
Yeah, I got it, sir. Got it. I got confused.
Sir, this one, like, I have a doubt,
Yes.
like why did we take like 1 and 2 as a like combination, like 1 times 1 comma 0 plus 2 times 1 comma 1.
Okay. So that we already discussed that what does it mean this coordinate 1 comma 2 with respect to the basis B2. So this means if let's say uh, this is let's say C1 and this is C2. So this means actually that this vector, whatever the vector we get, this can be represented by C1 into the first basis vector, C2 into the first basis vector. Okay, let me see if I have the with this here that I have the notes for the coordinate system. If you look back, coordinates, yeah, here, coordinates of a vector. So if B1, B2, Bn are the ordered basis, then if we say the coordinate of a vector is C1, C2, Cn, that means that vector is expressed by this linear combination Ci into Bi.
Sir, so that like okay, so that yeah, 1 comma 2, that vector is with respect to the B2 coordinate system. That's why are we writing.
So yeah, so that's why eh, you got the point that 1 comma 2, this coordinate is with respect to the B2
Yes, sir.
basis, B2 coordinate system. Okay, and we want to but get the coordinates with respect to the standard coordinate system.
Yes, sir.
Okay, is it fine?
Yes, sir.
Okay. So I'm going to show you this example because this is a little complicated example where we are changing the basis. Okay, and now we do the same thing for the other 1 comma 0 comma 1. So this we can get from the second column of this linear transformation. So that is 2 comma 1. But of course that will be also with respect to the basis B2. So this is 2 comma 1 but with respect to basis B2. And that means 2 into again 1 comma 0 plus 1 into 1 comma 1. And that means this is 3 comma 1. We do similarly the next one, and this we get 4 comma 0, but with respect to B2, that means 4 into 1 comma 0 plus 0 into 1 comma 1, and that is again 4 comma 0. So whatever we get here, this is with respect to the, that's a standard basis. BE, I mean by standard basis. Okay. Okay. Now, what was the reason to do that? The reason actually to do that, we had this equation 1, if you remember, this equation 1, and this equation is 1 is given here. The coordinates are with respect to the standard coordinate system. Okay, so now here we can apply, I mean, we can write down the value of t of 0 comma 1 comma 1, t of 1 comma 0 comma 1, t of 1 comma 1 comma 0. So that means now the equation 1 implies, we can say that t of x, y, z equals to c1 into 3 comma 2 plus c2 into 3 comma 1 plus c3 into 4 comma 0. Okay, now here if we simplify, it will be c1, that will 3c1, sorry, 3c1 plus 3c2 plus 4c3 comma 2c1 plus c2. Okay, fine, but we don't, the problem is, the good point is that now we get the linear transformation, but we don't know the value of c1, c2 and c3, right? So that we have to then figure it out, the value of c1, c2, c3. Deepak, please, can you mute? Deepak,
Sorry, sir.
yeah,
Sorry.
yeah. Please mute that. Thank you. Okay. So, but we don't know the value of C1, C2, and C3, right? So that we have to figure it out. Okay. So we have to figure out the value of C1, C2, C3 in terms of X, Y, Z. If we find the value of C1, C2, C3 in terms of X, Y, Z, then we get the formula for this linear transformation. And that's not difficult. Okay, let's put it 2. When we know the value, we'll put there. That's not difficult. Why? Because if you see here that this xyz in the standard coordinate system, it is, so here we had, let's say I give this number star, this first equation. Okay, so from this star, now we can get the value of c1, c2, c3 in terms of xyz. I just rewrite, don't worry, I rewrite that equation. So x, y, z was equal to c1 into 0 comma 1 comma 1 plus c2 into 1 comma 0 comma 1 plus c3 into 1 comma 1 comma 0. Okay, now what we can do, that left side and right side component wise we can make the equation, and we can say that x is equals to c1 plus, no, not c1, it is c2 plus c3, and y equals to, it will be c1 plus c3, and z equals to, it will be c1 plus c2. Okay, now if you solve this, just solve it, I mean it's not difficult to solve it. You will get the c1 is half of y plus z minus x, c2 is half of x plus z minus y, and c3 is half of x plus y minus z. Okay, now you apply this value in equation 2, and then equation 2 will become, if you make the simplification after using this value of C1, C2, C3, the equation 2 will become this 2x plus 2y plus z comma half of minus x plus y plus 3z. Okay, so whatever we get until now, this is the linear formula of the linear transformation with respect to the standard basis. Now we'll proceed further to figure out the matrix with respect to the given basis. But until now, whatever we have done, do you have any question or comments or doubts? Then we'll solve the rest of the problem. So whatever we have done until now, that we have figured out the formula of the linear transformation with respect to the standard basis or standard coordinate system. Okay, there is a significant lag from my tab to the display that I can see. Anyway, so is it fine until now?
Yes, sir.
Sir, so yeah, I
Yes.
just wanted to make sure so this T of x y z we are C1 C2 C3 they are we are just representing the transformation with respect to this T 0 comma 1 comma 1 T101 and T110, right, sir? Or
No. Okay. I hope that this is fixed. Okay. So this C1, C2, C3 that we in the first at the beginning we wrote that, let's say that x, y, z is a coordinate of a vector with respect to the standard coordinate system, and
standard, yes, sir.
C1, C2, C3 is the coordinate of the same vector with respect to the B3, that basis. Okay. So what is
Yes,
B3? B3 was, I have already scrolled out. Yes. So
yes, sir.
this one. Okay. So of course, since B3, the basis vectors are were this, that means the XYZ, the XYZ can be expressed as the linear combinations of this vector, and the linear combination, the constant multiplier will be C1, C2, C3. Okay, so
So sir,
these are
yeah,
the C1, C2, C3.
so this T0 comma 1 comma 1 all this these are in then B2, right, sir? Or then the transformed
Uh,
uh,
right. So now, so if we apply the transformation, so the left hand side is in the standard coordinate system, right?
yes,
And
sir.
now we apply, then the C1 is the constant. Now we T, so this 0 comma 1 comma 1, this is of course given in the standard coordinate system. Usually whatever
Yes, sir.
the value is given for a vector, if it is not mentioned, then you take that is with respect to the standard coordinate system. So
Yes,
that's why
sir.
we can, now we applying the linear transformation. But the problem is what we said, that we don't know the formula of T of 0 comma 1 comma 1. Okay. So now we want to figure it out, that what will be the value of the vector T 0 comma 1 comma 1. But what is given in the problem? It's given that the matrix for the linear transformation with respect to basis B3 to transforming a vector into B2 is given,
Yes,
right?
sir.
And we have seen that when you have the linear transformation from one basis to the another basis, how those matrices will be constructed. So this will be constructed, the transformations of the basis to the the coordinates will be with respect to the basis given on the right hand side, right?
Yes, sir.
And
Yes, sir.
And that's why here the transformation of t, if you take the first, let's take that means t of this vector will be transformed into a vector whose
V2.
coordinates are 1 and 2, but with respect to this basis
Yes, sir. Yeah.
b2. Right? So that we know. So that's why what we apply, that the transformation of this vector 1 comma 0 comma 1 is, or sorry, here the transformation of 0 comma 1 is 1 comma 2, but with respect to the basis b2.
Yes, sir.
But what we want in this formula, we want the vector with respect to the standard basis. And how to
Yes,
then
sir.
figure it out? Okay. So as we know that if this is the coordinate with respect to b2, is 1 comma 2 is the coordinate of b2. So that means from the concept of the definition of the coordinate system of a vector is this is 1 into the first vector of that basis, that is 1 comma 0, plus 2 into the second vector in that coordinate system or in that basis, right?
Yes.
And that gives us 3 comma 2 with respect to the standard
Standard.
basis, right? So now
Yes.
we know that if we apply that linear transformation, it will give us this vector 3 comma 2 with respect to the standard basis, and we figure it out
Yes.
for the other 3 vectors in B3. Okay, now we apply this into this equation 1. Okay, when we use in equation 1, the equation 1 becomes on the right hand side, it will only consist of this coordinates c1, c2 and c3. Fine.
Yes, sir. Yes, sir.
So until now what we get the linear transformation of xyz, and we get on the right hand side a vector, but the components are given with respect to the c1, c2 and c3. But this transformation is the formula with respect to the standard basis. Fine, but we don't know the value of c1, c2, c3. Now
Yes,
we
sir.
want to find the value of c1, c2, c3. How to do that? We know that this xyz, just if you go back from where we started, that the first equation, the xyz, the same vector with respect to the standard coordinate system, it is equals to c1, c2, c3 with respect to the b3 coordinate system, right?
Yes,
So
sir.
that means xyz, I have already scrolled down. Yes. So that means xyz equals to c1 into, that can be expressed as the linear combinations with respect to that basis, with the basis b3, c1 into the first basis vector in b3, c2 into the second basis vector in b3, and c3 into the third basis vector in b3. Fine.
Yes, sir. Yes, sir.
Now equating this, we get the value of c1, c2 and c3, and
Yes,
we
sir.
apply this value in equation 2, and then equation 2 becomes this equation. Let's write down this is equation 3.
Yes, sir.
Okay, fine. Any other question from anybody? Okay, if not, then we proceed further, but our goal is to figure it out. Now this is the linear transformation formula with respect to the standard basis, and we want to find the linear transformation matrix with respect to a given set of bases. Now the rest of the portion we already know, because we had an example in the last class. What we have to do that here, we have to figure out the formula for with respect to the basis from B3 prime to B2 prime. So that's why first we have to figure out the linear transformation we apply on each basis vector of B3 prime. So let's do that. So we now apply the first basis vector, that was 1 comma 1 comma 0. Oops, you can't see anything. I'm okay now. Okay, now you apply this formula, which is in 3, and we get 4 comma 0. Fine. But 4 comma 0 is in the standard coordinate system. We have to figure it out this 4 comma 0 with respect to the B2 prime coordinate system, right? We don't know the we know the basis vector, that means some constant into 1 0 plus some constant into 0 comma 1. Here it's easy to figure it out. We can apply 4, and then here we can apply minus 4. Okay, the next one, T1 comma 0 comma 1. Now apply the formula in equation 3. We'll get that this will transform as vector 3 comma 1. But again, we have to represent. Okay, so write down this is 4 comma minus 4 with respect to the basis B2 prime. Okay, so the second one also we have to write down the linear combinations of 1 comma 1 and 0 comma 1. Okay, now what will be this value? Here also it's not difficult to figure it out. We can apply 3, and then it is 3, we have to take minus 2. So that means this is the vector 3 comma minus 2 with respect to the basis B2 prime. Again, we take the linear transformation of the third one, that is T 0 comma 1 comma 1. This will becomes 3 comma 2, and 3 comma 2, it's also easy to figure it out in terms of the linear combination of this vector 1 comma 1 and 0 comma 1, such that we can give the constant multiplication of 3, that means 3 into 1 comma 1, and then minus 1 into 0 comma 1. So that means it is 3 comma minus 1 with respect to B2 prime. Is it fine?
Yes, sir.
Okay. Now the matrix will be now the I mean, like whatever our desired matrix, what we wanted to figure out, that is 4 minus 4, column wise we are writing 3 minus 2, 3 minus 1. This is the same linear transformation T is represented by this matrix, but this matrix is applied when the left hand side vector will be represented by coordinate system B3 prime, and it will give you a vector in R2, but the coordinate system will be with respect to B2 prime. Okay, is it fine, clear? Any doubt about this problem? Okay, I know that this was these are the examples which you if you know these examples, this then you'll have a clear idea that how to go from one place to the another place when the transformation is not given. I give you another example and give you the hint since we don't have much time left. Let's say that the linear transformation is from R3 to R2, and here matrix or any formula is not given. What is given? Given that if you take a vector in R3, they have given the three examples of the transformation. We take the vector in R3 0, 1, uh, sorry, sorry, this transformation is from R3 to R3. So here it is given that you take this vector 0, 1, 1, it will transform into 1, 0, 1. And you take the vector 1, 0, 1, it will transform into 2, 3, 4. Or you take the vector 1, 1, 0, it will transform into 1, 2, 3. Okay. Sorry. And let's say that you have to find the matrix. Matrix of T relative to the standard standard ordered basis. So that means we have to figure it out. What will be the matrix when the linear transformation is applied? On the left hand side, we take the standard basis. Right hand side also, we take the standard basis. But what I said that here the form neither the formula nor the matrix is given. So then in this case, how to figure it out? How to figure it out this one? So again, what we have to ultimately figure out, let's say that the standard bases are as usual we know that E1, E2, E3. And there our goal is to figure it out the T of E1. But we don't know the T of E1.
Sir, here the
On the other,
like the basis of domain and codomain are given, or like, or are we taking it to be?
right.
Yeah.
The domain and codomain both uh, the standard ordered
Okay,
basis.
sir.
With respect to that, we have to figure out the matrix. Okay.
Okay, sir.
But they are the linear transformation given with three examples. They have not given any formula or neither any matrix. Of course, we have to figure out the matrix for the standard. Okay. So here, so that means 0, what is given 0, 1, 1. We express this as a linear combination of E1 and the E2 and E3. So it will be E1 plus E2, right? Okay, let's say that we write down this is X. Let's say that Y is 1, 0, 1, and this is then your E1 plus, sorry, I made a mistake. The first one is not E1 plus E2. This will be
E2 plus E3.
right, E2 plus E3. E2 plus E3. And then second one is E1 plus E3. And let's say we write down Z equals to 1, 1, 0. And that will be E1 plus E2. If this is the case, then from here we can easily figure it out that E1, E2, E3 in terms of x, y, z. And if you just equate, it's not difficult to figure out. This is minus x plus y plus z. E2 will be in the similarly the half of x minus y plus z. Sorry. And E3 will be half of x plus y minus z. Okay. Now, when you know, now we figure it out. Then we can apply on E1 this linear transformation. Then TE1 will be half of minus T x plus T y plus T z. Right? And T of x is given. Where is it given? The first one. And T of y is given, T of z is given. Now we are just applying this. So then it will be minus 1 comma 0 comma 1 plus 2 comma 3 comma 4 plus 1 comma 2 comma 3, right? That's what we have, yes. And if you equate that, what you get, half minus 1, 3. It will be half 2, then it is 5, is 6. Okay, so I'm not completing the other two. So you figured out the what will be the value of other two at home, that what will be the value of TE2 and TE3. But then whatever the matrix it will be, the matrix will be 2 by 2 means 1, 5 by 2, and then 6 by 2. In the same way, that's the second column will be TE2 and third column will be TE3. Okay. Is it clear? Any doubt, question? Yes, Agnik, please.
So the TE1, the coordinates that is giving it is respect to the E1, E2, E3 or the basis that the original matrix T was giving in.
No, so what I told you that if it is not mentioned and the coordinate of a vector is given, if it is not mentioned that with respect to which basis, you just take it that this is usual, it's given with respect to the standard basis. So that means here the this transformation of these three vectors are given with respect to the standard basis, and on the right hand side after the transformation whatever the vectors we get, this also with respect to the standard basis.
Okay, sir.
Okay, any other question, comments, doubts? Okay, so if not, then we stop here. So
Sir,
we, yes,
yeah,
Rohan.
yeah, sir. So just one like, so here we are like we represented like E1, E2, and E3 as the linear combinations as of the given vectors, right, sir, in the
Uh,
domain.
no. So here actually the no, we are not dealing with any other basis. We are dealing with the standard basis. The transformation is given in that standard basis. Not the transformation, the vectors, the example vectors is given in the standard
Standard
basis.
basis.
And also we have to figure out the matrix of the transformation matrix with respect to the standard basis. But of course, to figure it out, we have to, the matrix will be, the first column will be TE1, second column will be TE2, and third column will be TE3. Right?
Yes, sir.
But
Yes, sir.
we don't know that when the E1 will be transformed, I mean, what will be the vector after the transformation of E1?
Yeah, so that's why
Because
we are.
we don't, right, we don't know the formula of the transformation, we don't know the matrix is not given. But what is given? The example of 3 transformation. Right?
Yes, sir.
So that's why we are expressing this E1, E2, E3 with respect to the given
Those. Yes,
vectors on the right hand side, right?
yes, sir. Yes, sir.
Because now if we can apply this transformation T on E1, since it's a linear transformation, if we apply T E1, that means it is T of half into minus x plus y plus z. And that means half into minus tx plus
Yes, sir.
ty
Yes, sir.
plus tz, right?
Yes, sir. And now we can represent here because it's given.
Right,
Yeah.
right. Yes, Gaurav?
Sir, in the first question,
Yes.
in the first example, sir. Sir,
So, first example, let's go to the first
yes, sir.
example. Yes.
Yes, sir. Sir, I wanted to ask that this matrix is given with respect to 0, 1, 1, 1, 0, 1, and 1, 1, 0
Right.
to B2, means from B3 to B2. So,
Hmm.
sir, here you are creating the transformation formula from standard to standard.
Right.
At
Standard
first.
to standard. At first, yes. Yes.
Yes, sir. Sir, I wanted to ask that if I could create the formula from B3 to standard, means
Yes,
I can,
you can
yes,
do
I
that.
can create.
You can do that. You can create. And later on, I mean, so here we are not uh, covering another area that is called the change of basis. So change of basis is another area of the linear transformation. There you can combine the linear transformation, also the changing of basis. It's only the matrix multiplication will be there. Then with respect to one matrix multiplication, you will be able to do that. That you take the vector in one basis, then you have the matrix. It will give you the in the another basis of your
The
desired
basis.
basis.
Yes. Sir, so
That
I
can be
was
done.
asking that, yes, sir. Yes, sir. So I was asking that, means if my coordinates are given in terms of B3, and with the help of this matrix, I can express in B2 because I just have to multiply that coordinates with this given matrix.
Right, right.
And then the final vector which I am getting in R2 in terms of B2, that I can express in terms of the general basis in R2. So what I told you that I did the linear transformation from B3 to R2 where the basis in R2 is general.
From B3 to R2, right, right.
So I was saying that instead of going to general, if I am doing it from B3 to general, and I am expressing those coordinates which was in B3 in terms of B3 dash, in terms of the basis in B3 dash, then I am going from B3 dash to general, because earlier I was going from B3 to general. Now I converted the B3 in terms of B3 dash.
Right, right.
And then now I am going from B3 dash to general, and I can then express that general in terms of B2 dash.
Right, right, right. So that means actually what you want to do, that you want to find, first of all, your main goal is to figure it out, of course, the matrix. But
Yes,
what
sir.
you have, first you had the uh,
B3.
B3,
Hmm.
right? And you then what you do that you, sorry, write down the 3 here, B3 prime, right? So you had B3 prime. So this will be your input vector here in the coded
Yes, sir.
system in B3 prime. Then you had some mechanism transform to B3, then a matrix which will give you uh, in the vector in B2, and from B2 another transformation will give you B2 prime, right?
Yes, sir.
Now this whole thing can be
By
done with respect to
multiplying
a
the
one single
different
matrix.
matrices in the intermediate steps. Yes.
Right. So here will be matrix, here will be a matrix, and here will be matrix. Just do that, and this matrix, then whatever the matrix, I mean, the multiplication of these three matrix will give you the same matrix
Okay, sir.
what we have figured out in that example. But you are right. I mean, that is actually the change of basis when you learn that these three matrix will be then multiplied and give you very easily. Then you can figure it out.
Yes, sir.
Yeah, Shankarashan.
So I had a simple doubt in the question number two that means can't we form the matrix using the vectors and just multiply with the inverse of this first matrix on both sides?
Sorry, can you please repeat your question? I could not get the point.
Means we are given three vectors on both the
You are given
sides.
three vectors,
So
both the
can't we
sides,
just
right?
form the matrices and multiply with the inverse of the first matrix on both sides to get the t?
I could not get your point. So that is our goal. That's what we are doing. That we are forming the matrix. But
No, means just using the properties of matrix.
how to do that? Can you just explain us?
Means the first matrix we will take t t into a equal to b, let's say. The a matrix we can take as 0 1 1 1 0 1 1 1 0 and multiply with the inverse of this on both sides.
Okay, so if I understood correctly, so you want to say that is it possible, let's say that I have a matrix A, then 0 1 1 is 1 0 1. This is the first equation, right? No, sorry. Uh, I'm writing in the different direction. It's better not to write in this direction. So you want to mean that 0 1 1 matrix A equals to 1 0 1.
No, no, sir.
Then the
The,
second equation,
the
no,
previous one was correct. Means I was saying that T into the matrix 3 cross 3 matrix is equal to the 3 cross 3 matrix on RHS.
T into that I cannot get it. T is a mapping, and mapping and matrix it's two different stuff, right? So how can you multiply a mapping with a matrix? I mean, of course, you can express the mapping in terms of a matrix. So, but anyway, so what do you want to say that this matrix into 0 1 1 equals to 1 1 0 1, right?
Yes.
But how can you write it? Means we apply the, okay, fine. Okay, let's write down first. 1 0 1 2 3 4 into 1 1 0. Then it's 1 2 3. Okay. Then what you want to do?
I was saying if we combine these three vectors to form the 3 cross 3 matrix, then
How to combine these three vectors as a 3 cross 3 matrix?
means first one we can take as column 1, second one column 2, and third one column 3.
Okay, easier question is, now probably I can get it. Easier question is that is it like this, that 0 1 1 1 0 1 1 1 0? Can we write like this? Is it your question?
Yes, sir.
2 3 4 1 2 3. Is it your question?
Yes, sir.
Uh,
Sir, you can combine these three
okay,
equations
so
to form that.
yes. Hmm. Yes, you can write this one, right? Um, yes, yes, you can write this one. Now your question is that now what you want to how to figure it out, that inverse
If
of then. Okay, so if you take then the A into that matrix, whatever the matrix is, you take the inverse and put it on the right hand side, right?
yes, yes,
But there will be one condition: if the inverse is not equals to non-matrix, right? I mean, so if the determinant of that matrix is not zero, then you can do that.
means non-singular matrices.
Non-singular matrices, yes.
Sir,
So
it
in
will be
each case,
non-singular because all the rows are independent and they form a basis. If they would be some sort of
right,
deep,
right,
yes,
right, 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 right. Yes, I mean, these are the linear independent vectors. If the linear independent vectors were not given, you were not able to figure it out the matrix A. That's true. Yes, you can do that. That's also possible.
Okay, sir.
Okay, yeah. A nice way to think this one in terms of the matrix equation. Okay,
sir.
any
Then A is my transformation matrix.
A is your transformation matrix, yes. So here there is no problem about, because there is no influence of other bases. So we don't need to take care of that part. Everything is happening with the standard basis. So that's why we can able to do this.
Sir, and for converting one basis to another,
Hmm.
sir, we just express that vector in that basis and just construct the matrix. Means, for example, if you want to express, suppose these three, some coordinate is given in terms of 0 1 1 1 0 1 and 1 1 0, the three
Hmm.
bases you chose, the three vectors you chose
Hmm.
in R3. Now I
Hmm.
want to express in terms of the uh, general
Hmm.
general
Hmm.
three vectors which form the
Hmm.
basis.
Hmm.
So I just express these three in terms of
Hmm.
E1, E2, E3,
Hmm. Hmm.
and from
Yeah.
there
So
I yes.
yeah, please carry on, and then I can tell you.
From there I means suppose 0 1 1 is there, I can
Hmm.
express it
Hmm.
in terms of some linear combination of E1, E2, E3,
Hmm.
and similarly for 101 and 110.
Hmm.
Then sir I make that matrix
You're right. Hmm.
such that now if one coordinate system is given to me c1, c2, c3 in this given basis 0 1 1 1 0 1, I just
Hmm,
multiply
hmm,
with that matrix to get the new coordinates in the general basis.
hmm.
So, sir,
Hmm.
that transformation is you taught it in a way, no? That
Yeah,
transformation,
yeah,
that change of
yeah,
basis.
yeah. So, right here within the example, it's already included. But if you're interested, you can read that chapter, the change of basis. Also, I can for you people, I can give you a link of a nice YouTube videos where not only the linear transformations, it's about the linear algebra. Different things have been explained in with the help of animations. But anyway, the main idea is that what you said, that if a vector is given with respect to one coordinate system, then we can able to construct a matrix such that if we multiply any vector in, let's say, the b1 basis, after the multiplication it will be transformed into a vector or coordinates into with respect to the b2 basis. Okay, so that can be represented, whole this transformation from one coordinate system to the another coordinate system can be represented in terms of a matrix. So that input vector will be from one coordinate system and then the output vector will be in the other coordinate system. So that is nothing to do with the linear transformation. That is just only the transformation of the coordinate system.
Sir, that change of basis you refer to, means you want us to refer to which book?
Okay, so if you among these three books, whatever the book you have comfortable with, you follow that one. So I suggested Mapas, then Gilbert Strong, and Kumaration. So whatever the book you feel comfortable, so you just read the change of basis from that book.
In that MAPA, I think it was not given
Mapa
in.
is not given. Okay, then Kumaration and Gilbert Strong you may consult with.
Sir, and you introduced us many matrices in R2, R2 to R2, like shear, rotation.
Yes, yes, yes.
So, do we need to also look up the R3 to R3 for those?
Uh, no, not at this moment. So these examples are sometimes necessary for, I mean, for different purposes as an application basis. But of course, when you go for the higher classes, there maybe when you think about the rotation and all those stuff, the reflection, there maybe you can think of R3 or in Rn. At this moment, R2 is fine.
Okay, sir.
Okay. So do you have any further question, comments, doubts? Okay. So if not, then I stop here and we see each other tomorrow.